Hello and welcome to another GCBASIC video. This is looking at the read-write modify solution that I've just completed. This is August 2025. The compiler is extremely old and there was a problem on the forum. Hugh wrote me a note and I have decided to fix it. So here we go. Let's go into the problem. So what is read-write modify? The general rule is that on PICs, legacy PICs, if you use and you try to write or read from GPIO, that's the input and output, or the port, that don't have a latch, they don't have this thing called LAT, A or B, whatever, and you carry out a bitwise write, it performs what's called a read-write modify write cycle, and that's I'll go into that and dig that into that a bit deeper. The microcontroller actually reads the pin state, it modifies the bits and writes it back, and you get potentially unintended results because the port or pin could be an input or it could be externally influenced by a motor or a capacitor. So you get examples, and an example would be when you say port or X1. So you want to get the state of a port, but in reality, it reads the state of the port, which could be actually unexpectedly high or unexpectedly low. And because it reads it in and then applies the rule of number one to it as an OR statement, it will just break it and you'll get bad results. And the bits will just move around. This is a very well-known problem. It is not an issue with the GCBASIC compiler, and it's the same on GPIO on some of the other chips, and we'll look into that in the baseline chips. So what you've got is a summary. If you're using GPIO and you're trying to do you could have a read-write modify issue on most 10s and 12s. You could get the same on a PORTX if it's a mid-range and it has not got a LATX. It hasn't got the register LATX. And if you've got LATX, it's not a problem because you can just handle it through the latch that's called LATX. So is this actually a fault internally within the microcontroller or within the assembly? Well, it is actually part of the hardware architecture. It's not explicit in your code that you're writing. It's a side effect of the PIC executing certain levels within the silicon itself. You ask it to do something, and internally it reads, and internally it misinterprets, and internally it writes back, giving you this issue. So what's actually happening is when you want to set bit 0 of a GPIO, internally, it reads the entire port, which reflects the current pin states, but they might not be where you think they are. It will modify that bit to set it and then write that back, overwriting whatever was there before. So you might think that you're writing to port 0, but it could actually write a different state to port 0, or it could actually write back different results into the other ports. This happens even though the instruction says, and only says, write bit 0. It's the way the internal logic works. These are all the instructions that actually trigger a read, write, modify. All these instructions read the entire register, modify the bits, and write it back. And as I say, they can cause unintended effects. And they are setting a bit, clearing a bit, incrementing a register, or decrementing a register, ORing something, ANDing something, XORing something, complementing it and rotating left or right. Any of these could have a potential side effect. Instructions that don't have this are things like moving W to the register, so it's moving something from an F register into a GPIO or clearing the port. They just don't have those issues. So what we're going to try and do is leverage that insight. We know that these two don't have that issue. So what I've done on my third attempt, because it's taken a lot, I I've written an adapter. It's within the compiler. You have to turn it on, but it's a new adapter, and it scans the assembly that's been generated for bit level operations like BCF or bit setf. So, setting these bits on these volatile ports like GPIO and port A or B. It's then going to redirect all the operations to a register, and I'm going to call that LATX for the time being. And I'm going to isolate that away from the hardware state. It's just a piece of RAM, 1 byte of RAM is going to hold a shadow register. We're going to track all the pending changes on the writes, and then we're going to flush those out when it's safe. So it handles conditional logic and toggling like GPIO, not to GPIO with multi-step rewrites. You could do it with one, but you will have the potential of a read-write modify issue. And what we're going to do is expand that out to make sure it's correct. Example. So on the left here, let me bring my pen up. We've got a write operation. Bit clear F, GPIO, bit 1. So GPIO clear bit 1. It's now going to change that. Oh, my formatting is not brilliant here. It's going to clear this LATA A. It's a RAM, piece of RAM. Clear, move. I'm sorry, I'll just clarify that. I'll just clear all that. It's going to ensure that the bit 1 is clear. It's going to move that to the W register, and then it's going to move that to the GPIO. It's a bit poor formatting. So this benefits by removing the read-write modify hazard. It's all done automatically. It should ensure port safe manipulation, and it produces maintainable and syntactic, it's correct as assembly. So let's have a look. So what we're going to do is we're going to look at this how you turn this on. It's going to be called option shadow register, and you can either put GPIO or port A or port B, and you don't have to have both, and I'll show you that. So we're going to go live into a demo. So what have we got here? Let me zoom in for you. I've got code for 16F 12F675, and I've turned on the shadow register. I've said shadow register the GPIO, and then all operations will be syntactically checked for read, write, modify, and updated. So why don't I just turn that off, press F6 just to compile the file, and then we'll have a look at the assembly. It's just compiling it. This is build 1490, and I'm using npasm to compile my assembly to make sure it's okay, right? You don't have to do that. So let's have a look at the assembly. And what have I got in here? I've got things like this, like I've got set GPIO bit 1 to 0, set GPIO 2 to 1, set GPIO 1 to 1. Lots of tests. These are just lots of tests of all the different cases. So let's have a look in the assembly. If I shut that one down, I'll just open up the assembly by pressing Shift F7, and here it is. And if we look in here for the first test, and here's test, and it's actually test 3. I wrote a note on this earlier on to myself, and test 1 and test 2 were rubbish. So because of the syntax and documentation, it's case 3 is the first one I started at. It says here, I want you to do a GPIO, set GPIO bit 1 to 0, and conventionally it will set it. It will go BCF GPIO set bit 1. That's a read-write modify issue. It will be corrupted. It stands a chance of being corrupted. This is one on bit 2. Back to bit 1, back to bit 2. All of these could be unsafe. Let's recompile that, turning on the shadow register. Just uncomment that, recompile. It will now recompile it for us. On the screen, it will just jink as it updates it. There we go. Great. So you saw it before the assembly had been completed. That's correct. So here's same thing. GPIO.1 bit 1, set it to 0, clear it. Is this where we were started? Yeah. Here it says right, clear LATA A, move LATA A to the W, and then move the W into that file, the GPIO. It does the same. It takes more steps. It doesn't matter because it resolves the read write modify issue. Let's have a look at something a bit more complex. Down here, it said set GPIO to 55. Well, that doesn't have a read write modify issue. Therefore, there is no code to be written. It just accepts it, and the tool ignores it. This adapter ignores it. But if you look at something like toggling a bit, a single bit, if we look at that and let's just turn off the shadow register for a moment, compile it. We'll look at the assembly in here to see what it was like without the new adapter. Just going to find it. It says in here, right, it says clear down a temporary register, a temporary variable. It says if bit 1 is set, increment that up by 1 and then invert it. And that's the way that GCBASIC does a not. And then it says, okay, clear GPIO1. If the clear it down, so it's now 0, it's turned off. Then it says if the systemp variable we're using on bit 0 is high, then go back and set it. So it always sort of manages to do it properly, okay? But did it do it properly? No, it didn't, because this is a read-write modify issue. This here is explicitly a read-write modify. So that will not work reliably. Control Z. I'm just going to recompile, and then we're going to do a search looking for exactly the same assembly. So it's case 8 we're looking for. There we go. There's case 8 again. This time, clears down temp, does the examination of the state of the IO, GPIO bit 1, and it increments it and comms it exactly as it was before, but these are safe operations because they're in RAM. Then it clears LATA A, and then it moves that down to the GPIO, exactly the same as it did with the GPIO directly, but this is an indirect movement, moving LATA A into W and then pushing it into GPIO. So we now know we've got an updated register. Now, in the context that every other LATA operation and GPIO write is inside LATA, it's what's the word I'm looking for? It will be consistent. Now we look at, we then set LATA 1 and we move that back down. And it's exactly the same test in here. We said, is the system 1, is it 0? If it's 0, then set the bit, okay? So we've got a way of adapting the assembly so that it works correctly. So GPIO here, that is a definite bad practice. That would have been a read-write modify. It now takes the LATA. It actually it does the comf on the LATA, then writes it back down to the GPIO. So an adapter, and it's managing all of this code. Does it automatically, and you can pass this into MP-ASM or into PICs. Doesn't really matter. Let's look at how it works on a 16F. I've got 2 shadow registers here. I can choose A or B. There may be others here, guys. I've only assumed port A and port B. There may be others that are impacted. I don't know. Let me know. So if I wanted to say I want to just shadow register A, I will look at the source in here. Shadow register A, compile that up. We'll look at the assembly. So we've only actually done it on port A, and we've got operations in here that refer to port A and port B, so we can compare. Open up the assembly. So we've turned on port A. We can tell that because look, it's created a LATA A variable for us. If you look at the bottom of the code, it's cleared it down so that you've got the same state as the register. Right, port A, it says port A, set it to 0, and it uses the LATA. It says, right, port A2, let's set LATA 2 to set that bit, and then move it down to port A. We've now got it working correctly. But look at port B. Port B is still using the direct risk, with the risks of read, write, modify. So this is a really good example of seeing them both side by side. If you want to turn on shadow register for that, just turn it on. It will only support GPIO port A and port B at the moment. Let's look at the assembly. We can now see that port A instantly changed to be a read, write, modify compatible. So that is the only change that you do need to do once you get this compiler is just say shadow register, and it will just turn it on. And down in here, it says, look, I'll just show you the compiler, optimize for read, write, modify. It gives you a hint. If you turn those both off, compiler, there's no message because it's not modified, and it's now read write. It now has the risk of doing read write modify. Now there may be bugs in this, there may be issues. Just let me know. That's the process we go through. So I'll try to get this out into your hands, and you can enjoy it. So that was a walkthrough of the read write modify solution with respect to GCBASIC. Thank you very much.